Okay, we're going to look at moment of inertia before we get into really rotational dynamics. So we've looked at torque, which is the rotational equivalent of force. We've looked at center of mass and equilibrium, so that's where your torques are balanced and nothing's accelerating. And now we're going to look at moment of inertia before we put everything together. One thing that you might see come up a little bit though is for point masses. The moment of inertia is going to equal mass times the radius squared. If you're looking at several different masses, you're going to look at the sum of rotational inertia. That's going to equal the sum of all of your mr squared. Again, this is not on the formula sheet. I don't know that they would expect you to have any of this memorized. I just wanted to show you how moment of inertia can be calculated and how it differs for different shapes. So I'm going to do the examples, just calculating moment of inertia. You have all of the equations right in front of you, so that's where those are coming from. And then that'll be all we're going to do, and then we'll put everything together next time with rotational dynamics. Okay, so number one, calculate the moment of inertia for each of the following objects. First, we have a bowling ball that has a mass of 6.5 kilograms and a radius of 0.15 meters. A bowling ball is a solid sphere, so that moment of inertia equals 2/5 mr squared. So that equals 2/5 times your mass, 6.5 kilograms times the radius, 0.15 meters squared. Multiplying this out, we get 0.0585 kilograms meters squared. Okay, next one, we have a 3 kilogram mass on the end of a 2 meter massless stick that rotates about the other end. So this would be a thin rod rotated about the end, where the moment of inertia equals 1/3 ml squared, L being the length of the rod. So this equals 1/3 times 3 kilograms times 2 meters squared, which equals, well, 1/3 of 3 is 1, so 2 squared is 4 kilograms meters squared. I'm not going to go through all of these because they are fairly straightforward. I do want to go down to the last one, so part D. We have a 4 kilogram disc that has a radius of 0.5 meters rotating about its center, and a 1.5 kilogram object sitting on the disc at a distance of 0.3 meters from the center. So if you have more than one object that's rotating, all you do for moment of inertia is add them. So just like if you have more than one mass in a system, you would add the masses. If you have more than one object rotating, you're going to add the moment of inertia. So for the disc, we're going to assume this is a solid cylinder or a disc. Moment of inertia equals 1/2 mr squared. So this equals 1/2 times 4 kilograms times 0.5 meters squared. Half of 4 is 2. 2 times 0.5 squared is going to give us 0.5 kilogram meters squared. So that's the moment of inertia for the disc. Now I need to look at the moment of inertia for the object sitting on the disc, so that would just be a point mass. So for a point mass, I equals mr squared. This equals 1.5 kilograms times 0.3 meters squared. So 0.135 kilogram meters squared. We're looking for the total moment of inertia. So the total moment of inertia, you're going to add all of the moments, just like you would add, let's say you were looking at an object, let's say you're looking at a meter stick and you have 2 masses on the meter stick. If you want the total mass, you would add up all of the masses. So for here, we're going to add up the moments of inertia. So your total moment of inertia equals, so I guess I can write the sum of the moment of inertia is equals 0.5 kilogram meters squared plus 0.135 kilogram meters squared. And that added together equals 0.635 kilogram meters squared. So the total moment of inertia is approximately 0.6 kilogram meters squared. And if you want to do part C as practice, I'll just give you the answer for that. It's similar to where you're adding up the moments of inertia. So you've got 2 masses on the end of a stick. So you would treat these as 2 point masses. The total moment of inertia for this one is equal to 7 kilograms meters squared. Okay, so that's it for moment of inertia. We'll be using this a lot when we get into rotational dynamics, so just make sure that you're comfortable with being able to calculate it once you're given the formula.